Alright, welcome everyone to 1.8. This is continuity, and this is the final section in chapter 1. So, for this first video, I want to talk a little bit, about continuity, this idea that we've probably brought up before. But we're going to be able to detect when a function is continuous and when it is not continuous, or another fancier term is discontinuous. And then we're going to use continuity, and it turns out these have something to do with limits. So we're going to be able to quickly evaluate out some limits. So, back in the day, right, we used to say something along the lines of a function is continuous if you can draw it without lifting your pencil. And yeah, this is true and a great intuitive definition, but we can be more precise now that we know something about limits. So, in this example right here, let's just get a little bit of a practice talking about continuity, right? So consider the graph of f of x to the right on the domain from -2 to 5. So I can go all the way down to the x value -2, all the way up to the x value 5, but that's where the function stops. Determine where the function is continuous. All right, so it looks like I could take my pencil and I could draw all the way up to 0, but then if I wanted to continue, I'd have to lift my pencil, right? So it's not continuous at 0. So I'm just going to go ahead and basically write some scratch notes here. X should not be equal to 0. And then let's see, what else? We go on, and then at 4, right, I'd have to lift my pencil to draw this dot down here. So it's not continuous at 4. You can see there's a hole. So x is not equal to 4. But besides those 2 points, it seems to be continuous everywhere else. So the question again is, where is the function continuous? Well, it would be all the way from -2 to 0. And then I'm using the parentheses to not include 0. I want to jump over 0, so I'm going to do a union from 0 to 4, not include 4 either, union from 4 to 5. So these are all the x values between -2, including -2, and 0, but not including 0. Then all the values from 0 to 4, not including either one of those, and then from 4 to 5, not including 4, but including 5. So this is where the function is continuous, right? I could draw it without lifting my pencil. More formally, right, so this is the old definition, a nice intuitive definition if we have a graph. But now that we know something about limits, let me give you kind of the formal definition. So a function f is continuous at a number a, number a, if and only if the limit, and notice that this is a two-sided limit, so as you approach from the left or from the right towards a for f of x, this should be equal to the function's value. So note, there's some additional subtleties here. So this requires, first of all, that there is a value, f of a, right? So this needs to be defined. And then also, it assumes that the two-sided limit exists. So notice if we go back up here, we can see that in this first case at 0, the left-hand limit and the right-hand limit are not equal to each other. So in this case, the two-sided limit doesn't exist, so it's not continuous. In the second case, the limit does exist. As you approach from the left and from the right, the limit exists. The limit would be equal to probably 3 in this case, right? 1, 2, 3. However, the function's value at 4 is not equal to 3. It's actually equal to here, right? This closed dot is at 1, height 1. So in this case, the limit and the function's value are not equal to each other. So you can kind of see how these limits actually kind of build on our intuitive idea of what is a continuous function. All right, so another definition, right? We often talk about continuity on an interval. So a function is continuous on an interval if it is continuous at each point on that interval. And then finally, a nice theorem. Essentially all the functions we love, polynomials, rational functions, root functions, trigonometric functions, are continuous everywhere in their domains. Let me give you an example. So a couple here. The limit as x goes to 0 for this nice rational function, right? This is a polynomial over a polynomial. Well, notice 0 is in its domain, so I can just go ahead and plug in 0 everywhere I see an x. So this is going to be 0 plus 3 times 0 minus 4 divided by 0 squared minus 1. So negative 4 divided by negative 1 is 4. Now we used to call this in 1.6 the direct substitution property, and this is kind of a little bit more formal, right, because the function is continuous. That's why we can go ahead. So in order to evaluate this limit, we know that that limit is going to be the same thing as the function's value, in this case at 0. Likewise, cosine. Cosine is defined everywhere, so if I want to figure out this limit, this is going to be 5, and cosine of pi, again, just plug in pi everywhere I see a t in this case, and cosine of pi is negative 1, so this is going to give me the answer of negative 5. So there are my two answers for these examples. So we can really evaluate out lots of limits very quickly now, using something a little more formal than direct substitution. It's actually because the function is continuous. All right, so one kind of upgrade that you might want to make is you might be interested in what about combinations of these beloved functions, right? So rational functions, root functions, trig functions, all these sorts of things. So if I have this one right here, right, which we have a trig function, and then inside of it we have a polynomial, we have a root function on the bottom, and another polynomial. So the question is, when we start combining these functions, is it still continuous, and does this theorem still apply? And the answer is yes. So let me go ahead and just plug this in. So this is going to be sine of 1 squared, that would be 1 plus 1, 2, divided by root 1 times 5 minus 1. So this is going to be sine of 2, and then 1 times 4, so that's going to be 4. And that's going to be my final answer here. Okay. So yes, combinations do work. And let me be a little bit more specific, right? The answer is, yeah, most of the time we are fine. More formally, if we have two functions, f and g, are continuous at a value a, and then we have a constant c, the following are also continuous at a. So as you would guess, if you were to sum two continuous functions, you get a continuous function. Likewise, if you were to take the difference of two continuous functions, you would get a continuous function. If you multiply a continuous function by a constant, if you were to take the product of two continuous functions, and finally, if you were to take the quotient of two continuous functions, f divided by g, of course, so long as we don't want g of a to be equal to 0. So long as g of a is not equal to 0, that's okay. It'll be continuous. Otherwise, you're dividing by 0, that's an issue. Likewise, if we have g is continuous at a value a, and f is continuous at g's evaluation at a, then the composite function, right, this kind of looks like fog here, but it's f composed with g, is given by, right, and that's just basically where you take g and you put it inside of f. This is continuous at a. So notice we use the majority of these theorems up here in this example without even knowing about it, right? Because we have a composition of functions. We have x squared plus 1 inside of a sine function. We are using that, hey, sine's a continuous function, this polynomial is a continuous function, this square root's a continuous function on its domain, right? We divided by stuff. So we actually use quite a bit of this without even knowing it. But these theorems right here, I mean, these can be proven, and it's just to kind of help us sleep at night, right? So that we won't break math by any means. All right, for our last example, I would like to determine where this function is continuous. And as you can see, we have a composition, right? So we have 1 minus x squared inside of a square root. We have division by another polynomial, in this case just x. But from all of our theorems up above, we know that this function should be continuous on its domain. So the big question is really an algebra question, and that is, what is the domain of this function? All right, so I need to think back. There were some kind of rules that we had when we were trying to think about domains of functions. One of them is that we don't like to divide by 0, right? So in this case, in order for me to divide by 0, I would have to have x is equal to 0. So I don't want that to happen, right? I don't want x to equal 0, otherwise I'd be dividing by 0, and that would not be in the domain of this function. A second big rule that we had when we were trying to figure out domains is that we don't want to have a negative inside of a square root. So that is, whatever I'm plugging into the square root, in this case 1 minus x squared, I want to make sure that that's not negative. So that is that it's 0 or bigger. Okay, so I don't want x to be equal to 0, and I need to know when is this true, right? When is this inequality true? So I'm going to use a technique in order to solve this inequality, in which we find first where this is equal to 0. Those would be good points. And then I'm going to kind of split up the real numbers into some intervals, some sub-intervals really, and choose some test points. So if you haven't seen this method before, this is going to be a great introduction, because we will use this a ton in this class. All right, so let me first figure out when this is equal to 0. So I'm going to add x squared to both sides, take the square root, and that'll give me plus or minus 1. Remember, when you take the square root, you have the plus and the minus. Next up, let me go ahead and draw the real number line here. And I'm going to use the places when it was equal to 0 to split up the number line. So I'm going to go ahead and write -1 here and 1 here. So now you can see that we've split up the number line into 3 kind of sub-intervals. We have the numbers that are smaller than -1. We have the numbers that are between -1 and 1, and we have the numbers that are greater than 1. And so I'm going to choose test points in each one of these intervals and try to figure out, is this inequality true on each one of those intervals, for each one of those test points. So let me go ahead and show you. Here's a test point, -2, that lives in the numbers that are less than -1. If I was to go ahead and plug in -2 into this inequality, I would have 1 minus -2 squared. -2 squared will be 4, and is that greater than or equal to 0? So 1 minus 4 would be -3. No, this is not. Put next to this, so it is not true at -2, and actually this test point will speak for the entire interval. I'll go into more detail why this works in a later video. Next up, let's choose a test point between -1 and 0. My favorite has got to be 0. So, okay, if I plugged in 0 into my inequality, 1 minus 0 squared, is that greater than or equal to 0? So 1 minus 0 is 1. Is that greater than or equal to 0? Absolutely. So this works out. Great. And then next up, one more. I'll use green again. I'll use black. All right. A number that's bigger than 1. So my test value will be, in fact, let me make a fun one, right? So this I would probably choose just like 2, right? And that's kind of boring. But let me choose a more interesting one. Maybe I'll choose 10, right? That's a number that's bigger than 1, just to really show you that you can choose any number in this interval as your test value, and it'll work. So, okay, 1 minus 10 squared will be 100. Is that greater than or equal to 0? Well, 1 minus 100, well, that's going to be -99. Is that greater than or equal to 0? Absolutely not. So the only place that this inequality holds true is between -1 and 1. So if I was to go ahead and maybe draw the solutions to this, right, between -1 and 1, and then the question is, what about at these endpoints here at -1 and 1? Well, we saw that was when actually this is equal to 0. And this inequality is when it's greater than or equal to 0. So I'm okay with equal to 0. So yep, let's go ahead and shade those in. Okay, so the domain of this numerator bit is between -1 and 1, and we don't want x to be equal to 0. So where is this function continuous? Well, it would be everywhere from -1 up to 0, but not including 0. Then we can continue on our way to 1. So this will be our final answer. This is where the function is continuous. All right, that is the end of our first video on continuity here in section 8. Next time we're going to be talking about cases where functions are not continuous. I'll see you then.